Hello, I'm Darren Jackal. I'm in my studio. I talk about product development, design, and mountaineering. Welcome to another episode of Experimental Design, Discourse, and Disclosure. Today I'm going to continue the series on lower extremity function and implications for footwear design. In today's episode, I'm hoping to wrap up and I will show you the work I did as a graduate student for a master's. And that should be viewed really as a conceptual design. There's really no real footwear involved. What you need to understand is that this is sort of the first iteration where we remove from the search space our initial solution space. And this is what I would consider to be a contraption. It sort of encompasses the ideas, the grand ideas that will go into a piece of footwear, but really it needs to be distilled down to more of an essence of what it needs to be. So what I'm going to show you at the beginning is going to be this initial idea and mainly an explanation model for discussing these concepts with my committee for my defense. Later, you'll see that during a PhD research period, I was developing different ideas around the same concept. And we'll get all into that in the next little bit. So stay tuned. I'm just going to use this proposal document to do a quick review of what I'm thinking of for this footwear design. Footwear that is either only rigid or only flexible may cause discomfort and or injury during demanding activity, and footwear for demanding activity should mimic foot structure and behavior by changing from a rigid to flexible structure, changing from a beam to truss action, and by changing shape, as the foot can be based upon three general segments, that is the rear foot, forefoot, and toes, so should the footwear. So we've used our search space to generate an original solution space, and that's the model I'm going to show you. And what my thinking is that this solution is going to actually be climbing a taller mountain than what I believe to be the sub-peak of the rigid boot and the flexible boot. I think a boot that can be both rigid and flexible depending upon the performance demands will be a much better concept. So what I need to do is get it out of here and into the hands of my users, because there will be things in the weighted matrix that can only be determined by a user, things like comfort and performance and fit. So this is just as part of the iterative cycle, and what I can show you here is an early sketch of showing sort of what I consider to be the intimate relationship between the foot and the footwear. I kind of see this idea of a chassis that basically envelops your lower extremity and functions in the same exact way that your foot does, depending upon the instantaneous performance that is being required. The model I will be demonstrating with is pretty abstract, and this document sort of takes that abstraction and tries to put these ideas into a form that represents more of a real product and how you would go about creating such a thing. So I'm not going to use this document to just explain much, because the model will do that for me. I need to wrap this thing up for my defense, and I'm trying to figure out how am I going to explain these ideas. And I really can't build footwear because I really don't have real feet at my disposal. So I'm thinking, well, I've got these conceptual feet. I'll use the conceptual feet to create conceptual model of the footwear. What this is me returning this original foot back into the coordinate cage that I used to generate the form by placing the axes of rotation that are important into this coordinate system. What you need to understand is that this is foot and footwear combined into this integral structure that has the rear foot component held in place by the cage, in the fact that the subtalar joint and the transverse tarsal joint are connected directly to it. So you need to think of this as the whole rear foot segment. Then there is the forefoot segment, which is between this component and these spheres here. So this is all considered to be a single sort of segment of footwear, and then you have the toes, and then there's the shank, which there's another coordinate system here you can see that illustrates the shank component and what the cuff would look like, or the cuff would, how it would behave. So now what I need to demonstrate is that I have motion, independent motion at the subtalar and the ankle joint. I have independent motion here at the transverse tarsal joint, which is the critical joint for allowing motion between the rear foot and the forefoot, so you can see that. And I have motion here at the toes. Now, depending on different circumstances, such as when my load is over my arches, in this situation, you can see that the system is designed to make that rigid. Okay, so no longer have motion at either my toes or at the forefoot. To allow motion at my toes, I need to relax the shank portion, and then I will get motion at the toes. And you can see when I crank that up, I don't get motion at the transverse tarsal joint, but if I relax that, now I can. So in certain instances, this structure is flexible, but in other instances, it's rigid. So this is the essence of the idea. This is all very complicated, and what I need to do in the next phase is reduce this to an essence and make it actually manufacturable. You'll see in the next portion where I determine that this axis is going to be, the transverse tarsal axis is going to be critical to that, and this is what I propose for the PhD, is to optimize the joint axis in individuals. I see this only working as customizable footwear, that mass production would really be difficult to do. And so I thought in the 90s that was 10 years away. 10 years later, I thought it was probably 20 years away. And now at this stage, it could be done. We do have the capabilities with 3D scanning and 3D modeling and 3D printing to probably create customizable footwear that would work with your foot to create the same shapes and the same structures that your foot does during demanding activity. So after this, I'll go in, I'll show you the work I was doing for the next phase during the PhD to optimize this joint. For the next portion to make sense, I gotta provide a little bit of background information. So I'll start with this document, the proposal. First part is the conclusion, number 3. Footwear that mimics the foot structure and behavior cannot be designed on a traditional static last. A new type of last that can match dynamic foot shape is needed. What I say I'm going to do is that I'm going to determine an optimal transverse tarsal joint axis for any foot using evolutionary computation. At this point, I have an advisor from computer science who's into evolutionary computation. This is where I begin this interest and research into using evolution as a basis for a design process. So next thing I say I'm going to do is to build an articulating last based upon an optimized transverse tarsal joint axes, and then I say I'm going to build footwear based on this new type of last, and I'm going to quantify it. And I never get around to this because things happen. Anyways, the Human Performance Lab is creating all kinds of interesting data, information, systems, methods, and I'm going to use a lot of their stuff in my work. One of them is a method for measuring foot shape and dimension that they developed. This was by Liu et al. In 1999, and they also developed a new reference system. They came up with a way of putting the foot into a grid that would allow it to be sort of standardized. So I'm going to use that. Benno Nig quantified relative arch deformation, and Lee used his information to assign subjects to one of 3 groups: a rigid foot type, a normal foot type, and a flexible foot type. So Lee is looking at relative motion between the forefoot and rear foot, and he marks the foot up and he does motion trials. He's got a bunch of data, and I'm able to get that data to create my mathematical model where I'm going to optimize the joint axes. And so the foot is marked in the manner described by Lee, and so this is the reference system that is used for that. But I'm going to simplify my simulation, and I'm going to create a new coordinate system based upon the line between marker A and B on the forefoot. And I'm going to just reorient my coordinate system to simplify things, and I'm going to put my rear foot segment, I'm going to make into or I'm going to model it as a sphere, and I'm going to line it with my coordinate system. Now this circle here represents the joint axes I'm going to test, and so this 4-foot segment, I'm going to rock it back and forth, but you'll see on my model I come up with a kind of a better way to do it, a more realistic way. I'm going to rock it back and forth so that point E moves up the way Lee describes. He says it augments the arch by 10.5 millimeters. So basically point E moves up 10.5 millimeters. And then what happens is when it's so that's going from T0 to T1. And at T1, we take a measurement between the markers on the medial aspect of the foot and then the lateral, and we compare them to what Lee has found. And we also compare the angle of the forefoot to the rear foot, and we look for the abduction and we compare it to what Lee found. And from that, we get a fitness score. And so the next trial is to, through evolutionary computation, change that joint axis and run the trial again. Now, I was doing this in a physics engine, 20 years ago, and it basically bogged down that engine every time this axis was, triplanar. So, but nowadays I would expect you to be able to find a computer that could run this trial and do those calculations incredibly quickly. And that's the thing with evolutionary computation, is that you're going through a lot of different potential solutions. You're using a Gaussian distribution. There's a whole method to do this, and so I'm going to follow those methods that are going to be described. But I will show you the mechanical version of this that I created to demonstrate to my committee to get them to sign off. The idea is that a traditional static last cannot be used to develop or design the type of footwear I'm looking for that will match dynamic foot shape. So what I want to do is I want to take this static last, convert it into a dynamic last, and the important axis of rotation I need to have in it is this transverse tarsal joint axis that will allow motion between the rear foot and the forefoot. So I'm going to use systems designed by Nig and Lee and Liu to mark our foot using the reference system to then create a digital model that I will put in the computer, and this is basically a mock-up of what that would be. So this is the point on the navicular that's going to raise 10.5 millimeters, and I'm going to measure between these points and these points back here, and we'll measure the angle, and then we'll compare that to Lee's, and we'll get a fitness score. Okay, so it's going to go up, we'll do the measurements, go back down, change this angle through using evolutionary computation, a mutation, Gaussian distribution, where small changes happen, but then every once in a while big changes happen, and we will just continue to run them until we get essentially no better solutions or we get a perfect solution. So every trial will be up, measure, back down, change, up, measure, and then so if we get a better result than last time, we continue with it. If we don't, we go back to the previous one and we mutate that one again. This episode is getting to be a bit long, so I'm going to stop it here. This sort of wraps up my discussion on the work I was doing, as an accidental academic, and that never really went anywhere. So it's now out there. It is what it is. So maybe I'll do another episode where I talk about the implications of this idea for something like ski mountaineering, which is more my interest nowadays than the alpine climbing I was doing when I was much younger. So stay tuned for that. I'm Darren Jackal. I'm in my studio. I talk about design, product development, and mountaineering. Thanks again for stopping by. This has been Experimental Design, Discourse, and Disclosure.